So let's do a quick recap of where we are at. So basically the whole week 3, we learned about the 2 key concepts of electric field and electric potential. It's basically 2 different ways of answering the question of why things move, or how do things move, right? Why or how do things move? The things we want to analyze about motion. So the idea of electric field is saying that as long as you have some source, that basically any sort of charge would create a field, and the field would move other things by move other things that has charge. So basically if you have a charge, it will create a field. The field would move other charges by providing a force that is proportional to the field and the charge that you're trying to move. And then we're taking these concepts to apply it to one of the most direct application of electricity, right? It's electric circuits. And we basically say that a battery is providing that job. And let's draw it, let's draw both terminals on this side. And if you connect it with a wire like this, in that picture, in the field picture, is what you're saying is you're providing an electric field. So these are the field lines in the wire. So every positive charge would start flowing this way. Okay, and we mentioned in yesterday's lecture, in real life, the positive charges don't actually flow. This is a historical misnomer. People thought, people just go like, oh, one of them is flowing. Let's just assume the positive charges are flowing around, until they discover that the positive charges, or the way they define what's called a positive charge, is actually bound inside the nucleus. And then the electron that's on the outside is actually more mobile. It's less loosely bound to the metal or the material. And those are what's actually flowing. So technically, once you build up the electric field, it's a really annoying historical fact that the electrons would go the other, so the electrons would go against the electric field because they're negatively charged. All right, so that's one picture, but as you can see, to draw the field lines in a wire like this, it's going to be very, very annoying. And also it's hard to work with because it's a vector. So we introduced electric potential, which says that any sources will basically generate a potential quote unquote field, not field in the technical sense, but field in the sense that there's a potential at everywhere in space. So it creates a potential, in some sense, a potential gradient. I think field is the best word. Unfortunately, it's also the technical word there. So and then how other positive charges, again, we'll focus on positive charges, put our mindsets back in the pre-electron discovery age. And I always find it's amazing that all these electricity theories and circuits and applications are discovered even before the electron was discovered. It's pretty amazing to me whenever I think about it. So the positive charges would move from high potential to low potential. So we have a easier way to think about this is if you create a battery, and we defined this yesterday. Battery is basically very simple to a physicist. We don't care about all the chemical reactions inside. We just care about the 2 terminals. It's basically something that creates a potential difference. Okay, you can look through the actual wording of that, but it's just a device that creates a potential difference. So let's say if this is a 9-volt battery, it's just saying that between the 2 terminals, if I say the EMF, right, that's the maximum potential difference it can create. Between the 2 terminals, it's creating a 9-volt difference. So let's say this is positive, this is a negative terminal, and this, let's call it 9 volts, and this is 0 volts. Okay. So as you know, it's only the potential difference that causes motion, right? The absolute potential doesn't really do anything. It doesn't affect any type of physics at all. It's almost like in gravity, where you're setting the ground level. You can set the top of a building as 0, and anything below that as -3 meters, -5 meters, or you can set the ground as 0 and anything above. It's only what's the difference in height that affects how fast you will fall if you jump off the building, you know, that kind of thing. So if it's a 9-volt, let's just for convenience set one of them is 0, one of them for 9. Oh, actually these numbers don't really matter. It's just for convenience to visualize, because now I can visualize all the positive charges here. Well, as long as you connect the battery and close the circuit, then they will start moving from the high potential to low potential. So you should imagine that the positive charge cannot go inside the battery. Again, this is a very schematic way of thinking, because remember, it's all very schematic because it's not really what the electrons are doing, but it's a very simple way, without going into the microscopic details of how electron moves, you will be able to analyze electricity like that. Okay, so how much it moves is described by current, which is how much charge per unit time it goes through a given point. So I can pick a point and then see how much charge goes through. Now, this is different from the idea of drift velocity, as we mentioned, because drift velocity is actually the actual speed or actual velocity that they drift around, that they move around the circuit. And it's actually extremely, extremely slow, which is a surprise whenever the first time I learned about it as well. So if you put a light bulb here, and we realize the reason it lights up so instantaneously, as long as you close the circuit, is that because it's not because this positive charge has went from the one side of the battery through to the other side and passed through the light bulb, not at all. It's really just because the wire is full of charges, and as soon as you set up the potential difference, everything feels the potential difference at the same time. It's almost like an ideal traffic scenario where you're at a traffic light, and as soon as the light turns green, every single car moves at the same time. They feel the green light at the same. Of course, this is far from the truth in real traffic. But in an ideal wire, this is what's happening. So almost every car is reacting to that green light, and every car starts moving. So it's not that the car from the very back of the traffic line is moving to the front. It's really everything is moving at the same time, so the lights will get reactive because this electron already this charge starts passing through its tungsten wire and creating that friction and creating that light. Some of you said the speed of light. That is actually correct, not for the drift velocity, but for the reaction time of that. As soon as if I have a switch over here, and as soon as I close the switch, so first it's open, and then as soon as it closes the switch, then then everything feels everything will feel that potential difference being set up at the speed of light. Okay. A quick comment about the language over here, because I'm aware there's a lot of international students here as well. So just a quick comment of the language, because in the upcoming homework, you may see sometimes it'll say analyze it when the switch is open or closed. So just remember, especially a lot of Asian language, open means turn on. It's the same word, especially in Chinese that I know, it means turn on, but in English, just be careful when if you're an international student, if it says close, that's what it means by turn on. Okay, so you're closing the switch, but just be aware that don't get confused. In case you think open, it does not mean turn on. It's referring to the switch, not the circuit. Okay, all right. And one last terminology is the word voltage. Is probably the most confusing thing of all. Voltage means potential difference. It's literally just another word for potential difference. And potential difference is a mouthful to say, so people start saying voltage. And also things are potential and potential difference is measured in, so a certain point minus a certain point, right? It's measured in volts, so this seems like a good word to use. But be careful, that does, whenever you say voltage, it has to be across two points. And whenever you say current, the correct preposition is it's through one point. Okay, all right. So now you can see how some of the more abstract concepts manifest in here. And we also talked about resistance, and the two formulas is this. You add them up if they are in series, if the resistors are in series, and you add up the inverses, so the equivalent. Sometimes we use this symbol to denote it. So just do 1, 2, so that's the equivalent resistance of 1, 2, right? Or you can use R equivalent or whatever you like. If they're in series, you just add them up. If they are in parallel, like this, R1, R2, the equivalent resistance. So if you want to replace it with one big resistor, like this, that has the same resistance as this combination, you should use this formula to tell you. And we provided a proof for, especially for the second one. The first one is, I haven't proved it, but it's very straightforward. You can see from the book. Okay, so let's try, see if we can do some warm-up examples over here. Let's focus on these two first on the left. And if you have a notebook in front of you, a scrap paper, I'll give you a few minutes, maybe just 1 minute, and see if you can find the equivalent resistance of this scenario and this scenario. Okay, so I won't wait too long since it's a pretty straightforward one. The first one is just the equivalent. By the way, whenever you do these problems here, since this is more problem-solving centric for today's lesson, let me give you some problem-solving tips as well. Always start with labeling things, okay? So that whenever you write down this is also helpful for your presentation of solutions, your quality of presentation in the homework and in your tests. Because if you start just writing down numbers, it's hard to follow what number belongs to what. it's good if all the resistors are different, but if you have, for example, all of them is 5 ohms, then your equations will be full of just 1/5 plus 1/5, and then plus 5 plus 1/5. And there's no way for the grader to know which one is referring to what. So the first tip I'll give you is label components with names. What that means is, you'll see me do that for basically the rest of today, is for each resistors, I'll call them R1 and R2 like this. And now I can start talking about R1, 2 like this, right? And for each battery, I'll label them with its EMF like this. Okay. So the equivalent resistance, since this is in parallel, this is 1/R1 plus 1/R2. So start off your solution writing like this, then it's very clear. So you label everything here. So you see that everything in my steps, all the variables I use in my steps are actually matching with how I defined it on the diagram. So there's no what's so-called widow variables. Sometimes people call them widow variables, where you didn't, if you have a variable here that is not defined anywhere, it's just a mysterious symbol that appeared in your solution, and no one will know where the heck does that come from, right? So make sure all your variables are traceable in some sense. Okay, traceable. Okay, so now you can plug that in. This is 60, oh, sorry, that's meant to be ohms. So 60 ohms is the SI unit, so that's good. So plus 100, and just plug that in the calculator, and you can get that. This is in series, so you this one you just add them up directly like this. So this one's easy. It's just 160, and just put in the SI units at the end. Okay. All right. So now let's look at this one, and let me address a question at the end of last lecture. Is how do we consider things are parallel or in series? So let's give them names first of all, so we can talk about them easily. So let's call that R1, R2, R3. So R2 and R3 are in series or parallel? Are in parallel, right? And how about R1 and R2? Can you put in the chat, what do you think they are? Parallel. Very good, neither. Okay, so let me write down the proper definition of it as well. So when we say something is in parallel, if they are in parallel, they need to share the same, oops, sorry, something popped up on my computer. Okay. Sorry. So when we say something is parallel, they have to share the same starting point and ending point. Share the same starting point and ending point. Okay. So let's look at R2 and R3. So R2 starts here and ends here. Let me use blue. And R3 starts here and ends here, right? So these are the two resistors. But as we said, if this is an ideal wire, then the top orange point and the bottom orange point, sorry, something keeps popping up in my computer. The top orange point and the bottom orange point are basically the same point because there's no potential difference over here, right? Quick recap is any potential difference is given by Ohm's law. So if an ideal wire where there's zero resistance, then there's no potential difference between here, if there's no resistance between here. So these are basically, all the three orange points are basically the same potential as far as absolute potential is concerned. And similar over here, right? So all the blue points are of the same potential. Is there a potential difference between the orange and the blue? Yes, definitely, because there's a resistance in the middle. So there's definitely a potential difference between orange and blue, like this. But between the oranges and the blues, there's no difference. So they do share the same point and the same ending point. So they are absolutely in parallel. How about in series? The definition is there's no branching points between the two components. Then it's called series. Okay. So no branches between the two components. Technically, I should say electric components, whether it's a light bulb or a refrigerator or computer, these are electrical components, but I'll just drop the word electric, okay? So if you look at B over here, it's called the R1 and R2. Okay, so these, between them, so there's no branches between the two components, so between them is this part, right, from here to here. There is no extra branch that branches out, so this is called in series. Okay, so this is a good test of whether things are in series or not. Okay, I think I won't actually plug in all the numbers. You can try this as an exercise at home. Let me directly jump to a more complicated one over here. And if you get, so it looks scary like this, but all you have to do is do it in steps, okay? So first look for look for things that are in parallel or in series, okay? If they're in parallel and series, you know how to combine them. If they are neither, don't combine those as your first step. Try to combine something you know how to combine first. So for example, here, the 6 and the 8, don't start with combining that because we have no formula on how to combine that. They're neither in series or parallel, but 8 and 4 are in parallel, right? So that's the easy part. So start with that because you do have a formula to combine that. So let me give everything names: R1, R2, R3, R4, R5. This one's called little r already, so let's stick with that since they provided the name for me, right? And they also provided epsilon here for the battery, so I'm good with that. All right, so the first thing I notice is R3 and R4 in parallel, so that means 1 over R3, 4. The equivalence between 3 and 4 is this. Notice how important it is to label, oops, not 5, label your variables, because you might call this 3 and 4. Someone next to you, well, I guess not next to you nowadays, a different person at a different home taking the exam might call this different variable. So whoever's grading that, they'll grade this on if you combine this correctly. If you just wrote I don't even know what you will write if you don't have things labeled. But let's say you write something equivalent to 1 is 1 over 8 and plus 1 over 4. In this particular example, okay, probably this will work because each of the numbers are quite unique. So whoever's grading this, they see 8 and 4, they probably see that you're referring to this. And since this is in parallel, you use the correct formula, right? But imagine if there's more than 1 8, and then something else here is there's 2 other 8s and 4s. So someone else might be writing equivalent is 8 plus 4, and they are referring to this one, or, you know, and it's impossible to know whether you know the stuff or not. So here's the exam tip: if you want to score as much partial credits as much as possible, then try to make it as easy to trace, so traceable, right? So that's why I mentioned here, as easy to trace your variables as possible. Okay. So 3, 4 like this. Okay. And then you can plug that in, 8 plus 4 like this. So 4, you can think of it as 2 over 8, so multiply top and bottom by 2. Like that, so we have 3 over 8, so that means R3, 4, just reciprocate this, is 8 over 3. And the SI unit is almost, but I'm not done yet, so I'll just keep it as here, I won't put in the unit. So let's, now that you've combined these two, think of these two as one big resistor, with an equivalent resistance like this. Right? So you can think of this, should I redraw the whole thing? Okay, I'll quickly redraw the whole thing, like this. And if you first start out, and if this is confusing to you, feel free to actually draw every step out. R5. Like this, right? Okay, so now it's very clear what your next step of attack should be, right? Can you see something that is clearly either in parallel or series? Is R1 and R2 in parallel? Be careful. They are not in parallel, R1 and R2, because they should, if they're in parallel, they need to share the same starting point and ending point. Let's see. So R2 starts here, R1 starts here. Okay, that seems like it's the same potential, right? So they share the same starting point, but R2 ends here, R1 ends here. So clearly, this is not the same potential because there's a potential difference here, right? If they're connected by an ideal wire, then that's good. But here, they're separated out. So R1 is not in parallel with R2. R1 is not in parallel with R3, 4. R1 is in parallel with both of these because both of these, they start here and end here. R1 starts here and end here. Right? Does that make sense? Try to send a public message. Don't send me a private message so it's easier for everyone to see. There's a question say, is R2 and R3, 4 in series? Correct, exactly. So the next step, you don't want to start adding R5 or little r or R1. This is the one you should do. Okay, so now we can add so what should we call it? R2, 3, 4, right? So that's R2 plus R3, 4. So R2 is 6 plus R3, 4 is 8 over 3. Right? 6 is, let's multiply top and bottom by 3. So I have 18 over 3 plus 8 over 3. That's 26 over 3. Okay. And then, of course, you can use a calculator. I'm just trying to save time because calculator slows me down. All right, so now you can draw a new diagram. Put it here. After you've combined this, I'll do this slightly slower the first time, since this is the first example, like this. And once you get the hang of this, you don't have to redraw a diagram every time you combine something. But at first, if you're comfortable, you don't have to. If you feel that it's confusing, this is the best way to do it. Right now, it is clear that these are in parallel, so you can combine this. Let me not plug in all the numbers, but okay, so this is in parallel, so make sure you use this. So I won't plug in all the numbers, but you can do that. So after you've combined this, you have R1, 2, 3, 4, R5, little r, and now you can do them all at once, right? Because they're all in series now. So you can finish this off with just R, let's call it total, or R equivalence, or R overall, whatever you like to call it, as R1, 2, 3, 4 plus R5 plus little r. Okay. And plug in all the numbers in, you get. All right. Now, if I add to this question, what is the current that goes through here? Now let's analyze the current that goes through everything as well. Okay, so remember another tip, let me write that in pink. Another tip is usually current is the last to solve, because current is the most dependent. The concept is that current is the most dependent on what you have in the circuit. If you have a lot of things with very, very low resistance, then the current will be very large. You have a massive current that goes through. If you have lots of resistance, then the current will be very small. Okay, so current is the most dependent thing on what you put in your circuit. The potential difference, or the EMF, or the voltage, is the property of the battery. How powerful the chemical reaction is that generates that potential difference. Of course, in physics, we don't care about the chemical part. We just care about the potential difference that the end game, what potential difference it generates. Okay, so yeah, so that is the depending on the battery. And then how about the resistance? The resistance depends on the actual appliance, right? So these are you cannot control them, but the current is something you can control by putting more or less resistance in your circuit. Okay. So after you find this, maybe I'll use a new picture. I'll copy it to the next page. Okay, so your favorite, the equation that will be your friend is for the rest of this week will be this Ohm's law, because you'll be plugging in a lot of subscripts to it in order to use it. So the first thing you want to find is you want to find the I over here. Let's call it I overall. So if you want to find the overall current, then you need to find the overall potential difference and the overall resistance. Overall resistance is basically what we just calculated, right? So we know this. Okay. How about the overall current? Sorry, the overall potential difference. Well, then we can draw a delta V like this to find out. Let me zoom in a little bit more. Oops, never mind. I want to find the current that leaves the battery. So I will need the potential difference across this battery, which is 9. Okay, so you plug in 9 over here, plug in whatever number you got from before, and now you can find what the overall current here is. Let's call this IO overall, like this. Some questions here is, let's see. Right, there's a long chain of questions. If someone wants to rephrase that for me, then I can not need to read through everything. Okay, or hopefully it's answered already. Okay, so yeah, so that's how you can find this. All right, so now that I know the current at this point, the point leaving the battery, remember current is always at a point. The potential difference is across 2 points. What is the current, for example, here after the resistor, or here? So I'm going to claim that as long as it's in the same branch, the current will be the same. And the reason is because if the current, for example, here is smaller than the current here, that means if the current is moving fast, if there's more charge per unit time going here than here, then what will happen to the charge? It will be like a very bad traffic jam in LA, because the charges will start piling up, right? So if you want a smooth, constant, steady circuit like this, then every current here must be the same value. So the amount of charge per unit time has to flow constantly. So here, all these excess that I put here has to be the same current. Now, how about here? Now it will be different, because this is now like I think the traffic or the freeway analogy is perfect, because if your freeway starts splitting up in 2, so if you're going down the 405 here and it splits into the 5 and the 15 or whatever, then the current, how many cars per unit time or how many charge per unit time will start splitting up, right? So if I label it in orange here, let's call this I1 and I2, the current through this part, then we have a simple relation that I naught is equals to, or I overall, IO is equals to I1 plus I2, right? So they'll get split up this way. And here you can, for each branch, every time it splits up, you will have a different current. So here, let's call it I3 and I4, and you can get a relationship here. This is I2, so I2 will equals to I3 plus I4. Okay. So what happens here? What is this? I could give this another name. I could give this a name like I5, but it's unnecessary because I2 gets split up into I3 and I4. So however many charges, let's say there's 100 charge per second going through here. Let's say it splits into 60-40. And then what happens is they recombine over here. So instead of giving a new name, let me just call it I2. Okay, so there's no need to give this a new name. You can, but then you will have an equation over here where it's I3 plus I4 equals I5, right? I3 plus I4 equals I5, so I2 equals I5, right? So that's in principle, if you know, after a few times you do these problems, you'll see that you can directly go like that. And then I1 plus I2 will go back here. So remember, I1 plus I2 is I overall, right? And as it should be, because this is the same branch as where it started. Okay? So this is how you can label everything. So let's say you want to find, all right, so let's say you want to find the current over here, okay, I1. Let's do this one at a time. If you want to find I1, then you will want to use your trusted friend over here, Ohm's law again, and put in the subscript 1 for everything, okay? And ask yourself, what do I know over here? This is your goal, okay? Do I know R1? Yes, I know R1. Do I know delta V1? Okay, this I don't know. So let's label that. Remember, every time you label delta V1, you want to label across it a certain device like that. So what is this potential difference? Okay, so here's another tip is whenever I get complex circuits like this, I like to linearize it. What that means is I want to make it so that everything almost goes in one line like this. So this is the little r's, and it splits up into R1, R2, R2 splits into R3 and R4. And they recombine with R1 and go to R5. So now you see everything is in one line, and this is what I call linearizing it. I can put the battery down here, but all my components, all my electrical components, all my resistors are here in one straight line. So this is the easiest way to tell. So this is another tip, right? So let's call this overall voltage, right? This is 9 volts, the overall EMF. And what I need now is to find delta V1. Okay, so let me actually extend my arrows, extend my brackets all the way to here, might as well, because if it's an ideal wire, it doesn't matter where put it here or here, because this is the same potential, right? There's no potential difference between here. Okay, so if I know the battery is 9 volts over here, how can I find this? Well, I probably first need to know this and this. Let's call that little r. Okay. So the battery is providing a positive, because a battery provides energy, right? So remember, potential is basically energy per unit charge, right? Work done per unit charge, as you know from today. So the battery provides this amount of potential energy per unit charge, and each resistor starts consuming the energy, okay? So actually, this is a good point to start. Let's actually label all the potential difference across each component, and we can try to derive the relationship between them. Like this, okay. So before we plug in numbers, let's see if we can derive some relationships here. So you can see that here, delta V3 and delta V4 shares the same starting point and ending point. So delta V3 must be the same as delta V4. So this is the first relationship you can write out. Okay, oops, that should be 4. Okay, so also now you look at this, delta V1 looks like it should be delta V2 plus delta V4, because let's say this guy consumes how much potential? Let's say this guy consumes 5 volts. So the potential difference between the start and the end is -5, let's say. Then because this is the same starting point and same ending point, here, these must add up to the same potential difference over here. They cannot be different. So maybe if I write it out, it'll be clear. So the potential difference between V1 should be V2 plus V4. Of course, you can also write it as V2 plus V3, because V4 and V3 is the same thing. So with this bracket notation, it is a great way to be able to identify all the different relationships over here. Okay. All right, so now you can also see that this potential difference plus this potential difference plus this one, right? These two are basically the same point. These two are basically the same point as far if the wire is ideal, right? If this is an ideal wire. So this plus this must equals to this. So even before you plug in the numbers, maybe a good idea is to label all these and write down all the relationships like this. Okay. Of course, if you like, you can say that V overall is VO over here is delta VR. I will not read the word delta, but you know that it's there. So this you can write it as VR plus V2 plus V4 plus V5. That is fine because that's the same. V1 is V2 plus V4, right? So, or you can write it as VR is equals to V2 plus V3 plus V5, right? So because V3 and V4 is the same. Okay. So there's many different relations. So after maybe what I would do is, if I were you, is I'll put a star next to this diagram because this is the best way to label things. It's almost like a free body diagram, kind of as important as a free body diagram when you do forces, the way you label this. Okay. So once you have all these relationships, let's go back to my original question. I want to find I1, which means, because remember, I is always the most dependent thing out of other things. So you usually want to find a current last. So you want to find delta V1, right? How do I find delta V1? So the first one is useless. This one doesn't provide anything about delta V1. I can either use this or this. Let's take off things that I know. So I know this is 9 volts, all right? So maybe, since I don't know anything about 2 or 3 or 4, let's look at this. Do I know what this is and what this is? So let's use our trusted Ohm's law again, right? But don't just write IR because this is confusing. So make sure you label it. This is the little r. This is for I5, right? So do I know R5? Yes. Do I know little r? Yes. Sorry, it's a little confusing. Maybe I should just write little r, but you get the point. And now do I know the current through here? We use orange. Do I know the current through here? So let's write an arrow instead. And do I know the current through here? Yes, as we talked about earlier, because the current has to be going at a steady pace. So that is basically just I naught. So once you found I naught from here, this is basically I naught, well, IO. So you know all this, and now you can find delta V1. And once you've got delta V1, you can plug that in here and find I1. So you see, usually I is the last thing to find in every step. You plug in, you find the delta V first and the R's first to determine the I's, which helps you find another delta V, which helps you find another I. So every time the I is usually the last step to find, okay? And so I'll leave it as an exercise for you to complete this, to find the I through the resistor 1, I through resistor 2, I through resistor 3, and I through resistor 4. I keep writing 4 as 5 today. I don't know what's wrong with me. Yeah, so try to find out what all these are. Okay. All right. And so after this, let's switch to a different type of example. Let's look a little bit about maybe something even more connected to real life, and to see how analyzing all these weird circuit things would help. So here's an example that actually is quite realistic. Imagine you actually buy a light bulb from Europe, and if you don't know, in Europe actually all the outage and your electric outage in all your plugs are given in around 240 volts, 230 to 240, and in the United States between 110 to 120. Okay, if you're interested, there's a map of which countries use between 220 to 240, and which countries use from around 100 to 120. So it's due to purely historical reasons that this is true. And at the week 5, at the end, once we learn about magnetism as well, you'll be able to see why this is the way it is, why this happens. But then again, also, this is the number of countries that uses Fahrenheit and the number of countries that uses Celsius. So there's that as well. All right, so if you buy a light bulb there and you try to plug it into a United States plug, what will happen? Will the brightness change? How do we analyze what will happen to the brightness over here? So first of all, understand that brightness is proportional to the power consumed. And this is easy to understand because brightness should be proportional to how much energy output of the light, of the bulb, right? The more energy it produces, the brighter it is. And how much energy per unit time is proportional to power. So so basically, if it asks for what happens to the brightness, so here's the question is, how bright would it be, right? Compared to a light bulb with 120 volts, is you want to calculate the power. Okay, so let's draw a diagram over here. Is if you have a light bulb, you plug it into something that is, so this is 75 watts, that's the power. So this is originally it's designed for example, 240 volts, like that. Okay. And now okay, so how does it provide, what is, now when you replug this into a different battery with 120 volts, what stays constant between these two? Okay. Between the light bulb itself doesn't change, right? What is really generating the light is the resistance. So it's the resistance do not change from here to here. Okay, so let's call this delta V prime. Okay, so the resistance here is R. The resistance here is also R. Okay, so so first we need to find out what the resistance is. So if I'm given the power, we know that from this equation that we can find the resistance. So if this is 75, actually this tells me the current. So if you plug it in Europe, then how much current will it draw? It will draw 240, 75 divided by 240. So let's plug that in. 75 divided by 240. So you're getting, it's drawing 0.31 amps, let's say, going through it. So what's the resistance? So let's draw the delta V over here. What's the potential difference across it? V equals IR. So the resistance of the bulb, it's the current through the bulb and the potential difference across the bulb. So if you're just connecting it through one battery like this, then this is also 240. And we just got this is 0.31. So now I can find the resistance of the bulb is 240 divided by this number. So the resistance is 768 ohms. Okay, so this does not change. Okay, so let's see now with a new voltage, with a new potential difference that you plug in, what will the new power be? So the aim is to find out new power. Okay, so to find a new power, you need the new current and the new potential difference, right? So the new potential difference is 120. So you just need the new current through here. Okay, so to find the current, remember you use Ohm's law to find it. Okay, so let's put a prime above everything, but the resistance does not change. So that one I don't need to put a prime across. Okay, so this is my aim. The I is usually the last thing to find. All right, what is the potential difference across this? Well, it's across the bulb, it's the same as this. If you're just plugging one thing into the wall. So you have 120 on this side, and you have I prime, the new current that goes through this bulb, and the resistance does not change because it's the same bulb, right? So remember 10 minutes ago, I mentioned the resistance is the property of the device, of the component. Okay, so we can find I prime is 120 divided by this. So it's 0.156. Okay. And therefore the power, the new power that it's generating is 0.156 times 120. That times 120, and it is 18.7 watts. So how much brighter is it, or how much dimmer is it if you do it this way? So if you look at this, divide by 75, the original wattage is 0.25 or 1/4. So this is the detailed calculation. You'll see that basically it will be 25% dimmer, or sorry, it's 75% dimmer, or it's 25% its brightness compared to if you use it in Europe. Okay, so that's not too bad, but the reverse is actually worse. If you take a US light bulb and plug in a Europe outage, then it'll be 4 times, it'll be the other way around, right? It'll be 4 times brighter and you might break the bulb that way. So this is why I don't know how many of you have traveled to Europe or other parts of the world where it uses the other wattage. If you buy devices in the US, they do not work in other countries. You need to buy the proper device with the proper that can handle a certain voltage in that country. So this is something practical that you learn from here after the whole pandemic is over, when you start traveling again. There's an easier way to get this result is you can think of, if you're very familiar with all the equations, then you may also remember this relation. You can actually combine the Ohm's law into the definition of power, the definition of electric power, and realize that the resistance of the light bulb is the same wherever it goes. Resistance is a property of that bulb. So if the voltage decreased by a factor of 2, then a square means the power will decrease by a factor of 4. Yes. So that's an easy way to immediately get the answer. But I want to also show you how to do the math throughout if you need. Okay. So here it might raise a question that why am I just plugging this alone to the outlet? In our home, don't we plug in a lot of appliances? So here's another practical example. In our home, we probably plug in a lot of different things, not only one light bulb. Okay, hopefully Zoom is reacting quicker. The lag is kind of bugging me. Yeah, so we plug in a lot of things like this, right? So isn't my analysis a little bit too simplistic? Well, yes, yes and no. The no part is because what we learn about parallel circuits, and that's the beauty of it, is if you have same battery like this, you can connect to a lot of different devices. One of them can be a light bulb, another can be a hairdryer, another can be a heater, whatever. So these are all different resistance. But let's say this is the power that comes from the power company. It's 120 volts like this, right? And look at the arrows. You see that the potential difference between here from the, I don't know why I keep writing 5 or 4 tonight. So, all right. The beauty of parallel circuits is so that everything has the same voltage, right? So you see that this point, this point, this point, this point, they're basically connected by ideal wires, right? So all of these are basically this point. All the orange points are the same, and all the green points are of the same potential, right? So the battery is basically, if you want to put in positive and negative signs as well, the battery is basically providing that much potential difference, positive that much, and each of them is consuming that much potential difference between them. So remember, yesterday we also talked about power consumed and power produced. So if you calculate the P equals to I delta V here, you're calculating how much power this is producing. If you take the I in here and delta V over here, you're calculating the power that is consumed over there. Okay, so another practical application is you might be interested in what fuse you want to use. So what is a fuse? A fuse is basically a safety device. For those who don't know, this is the symbol. You draw a box through the wire. But in real life, the device it's just like there's a cylinder where there's a very thin wire over here. And the wire is very fragile in the middle, so that if you have a huge current that goes through, it will just break. Okay? And that will protect you from overloading a circuit. So usually if any one of you have played with fuses with your dad or whatever before, then you'll see that there are fuses that ranges from, for example, 15 amps, or even some that smaller, from 1 amp to 15 amp, maybe 30 amps like this, to depend on what fuse you buy. If suddenly there's a power surge, then they will just break, and so that there's not too much electricity charge, not too much current. Current is charged per unit time that's flowing through the wire, especially to protect you from short circuits. Right? What is a short circuit is this. If suddenly, for example, you take, let me use red, if you connected this point and this point without a resistor, okay? So let's say you have a fuse over here, a fuse box over here. You can Google some image, how does a fuse box looks like. And if you suddenly connected these 2 points without any resistance, then because there's such a low resistance with a huge potential difference across these 2 points, right? It's the same point as the orange and the green, then there'll be a huge current suddenly flowing through here, which will draw a huge current from here, right? So first of all, it will drain your battery very quickly, or the power company very quickly. And also, if this is not just a wire, if this is your left hand and your right hand, that you're touching it, because humans are 60% water, and water is a pretty good conductor. Skin is also not a bad conductor. It's an average conductor. So if you accidentally touch both sides, you might draw a huge current over here. If it has a less resistance than the other device, then you might get electrocuted. This is a safety device that will immediately break it, so that it cannot go through. Nowadays, so fuses are a more old school device. Nowadays, we use things called circuit breaker, which, as the name suggests, does the same job. But what it does, it basically triggers it to flip a switch. So all you need to do is go to the basement and flip the switch back. You don't have to actually go and buy a new fuse. But you can Google some image until around like 20 years ago. These are not as popular, and here's the old fuses. All right, so how do I know what fuse to use for each? So if you want to put a master fuse over here, and you want to put a fuse for each of the devices as well, just to protect yourself in case you suddenly short circuit something like this. So what fuse should you buy to put in here with these ratings of the different devices? So now you can calculate that if they are all connected in parallel, as you can see like this, each of them will share the same delta V. So this is going to be 120. So you just need to plug in the power. So let's rearrange this. Is power divided by delta V, right? So for the light bulb, you want to plug in 100 over 120. Plug that in a calculator. I've done that earlier. It's 0.83 amps. So all you have to do is buy, for example, a 1 amp fuse, and that will work pretty well for the light bulb. And so for the bulb, for the heater, you can see, let's plug in for the heater. That is 1800 over 120, and you can plug that in, and it's 15 amps. So you can buy a 15 amps fuse, or maybe one that is maybe 18 amps, a little bit higher just in case, and that would work, right? So you can go through, I'll leave it as an exercise. You can calculate for the rest what is the appropriate fuse to use. Okay, all right. So maybe should I skip this example? Okay, I'll skip this example. If I have time, I'll come back to it, because now I want to go back to, yeah, the board is lagging for me as well. This is a bit annoying, but yeah, I don't know what to do. All right, so now I'll move on to the second part of today, which is a more, to handle more complicated circuits, okay? So there's an extra example. If I have time, I'll come back to it. Okay. So it's called Kirchhoff's rule. Is to handle circuits that are, for example, like this, especially more if you have more than one battery, for example, 2 batteries, or with lots of loops. Okay. So this is a way to, yeah, I'll just show you the technique of this, and it's given in your textbook, chapter 26. So first of all, let's use a simple example like this first. Sorry, the board is quite lagging. All right, so if I have 2 batteries, now it starts to get complicated, because before it's very simple. One of them provides potential energy or potential difference, and everything consumes potential energy or potential difference, right? But now if you have 2, so there's 2 things providing, or does this contribute to it, or does it not contribute to it? So this is how you analyze it. Okay? So the first step is you try to linearize the whole diagram first. Now, if you have a loop like this, how do you linearize it? You pick a starting point somewhere. Okay, so let me pick, for example, this starting point. And because you know the current is going this way, so since one is positive, the longer side is positive, right? So it goes from positive to negative this way. So I'll try to linearize the loop that way. So first of all, I'll draw the first battery, but how do I know this is the first battery as soon as I draw it? I can't really tell, so make sure you label and give things names. Okay, so let's call this epsilon1, battery number 1, and call this R1, R2. They're all R, so each resistance is actually R, so this is one of the cases where it will actually be confusing if you don't label things. in your equations. So now that I've labeled all my battery and all my resistors, I can claim that this is without a doubt epsilon1, and then it'll go to R1. And if I want to, yeah, and then the next thing it hits, it's R2. And then the next thing it hits is a battery. So let me get the positive and negative terminal right. So it's the shorter leg first, and then the longer leg, and then R3, and then R4, and then it wraps all the way back. So I'm not going to draw this last bit where it's wrapped back. Okay, so technically it wraps all the way back like this, but we don't really need to draw it, and we just assume that it's understood that if my board starts to react from me erasing that, then this side is just connected back to this side. Okay. I see that it labels A and B over here. In fact, later it asks me for the potential difference between point A and point B. So let's label A and B on here. So A is the point between R1 and R2, and B is the point between R3 and R4, like this. Okay. So the next thing to draw is what's called a potential drop diagram. Okay. So after you learn how to draw the circuit diagram from before, how to draw those brackets, this is the second important type of diagram you need to learn in this part of the course. It's basically like the free body diagram of this chapter. Is you take your whole linearized circuit and put it on the x-axis. So the x-axis represents along the circuit, and the y-axis represents the potential. This is in fact the absolute potential. Okay. So assume that it starts off with 0 like this. So assume it starts with 0 volts. So what does epsilon1 do? Label everything, epsilon1, R1, R2, epsilon2, R3, R4. So this, at first this whole Kirchhoff's rule technique this whole technique is going to call Kirchhoff's rule, but it's a little bit overkill with a simple loop like this, but it's going to be very useful for double loops, as you'll see in the next example. So so let's say it started with 0. What does battery number 1 do? Epsilon1. What does it do? It provides 1.5 volts, and so what it does is by the end of the battery, it's going to raise the potential up to 1.5 volts, like this. How do I know it raises it? Because remember, batteries always provide potential energy, and potential energy is basically the same thing. The only difference is you multiply by the charge, right? So other than that, the potential is pretty much the same as potential energy. So batteries provide energy, so it raises the potential. Okay, so the potential difference is positive, like this. And you see this is a shorter leg and a longer leg. This is also a good way to, a good mnemonic to remember for yourself, that it follows the slope like this. So yeah, this is the way I remember it. So you see it follows this positive slope. So what happens between the end of the first battery and the beginning of R1? Well, this is an ideal wire, right? So remember, any potential difference is given by IR. So if the resistance, if this starts showing up over here, if the ideal wire resistance is 0, then there's no potential difference between these 2 points. So the potential stays constant. How about after the first resistor? Well, definitely, because now the resistance is not 0, so it will cause a potential drop. So that's why it's called a potential drop diagram. So there's no potential difference between these 2 points, but there is a potential difference after the first resistor because there's a resistance over here, right? So it will drop over here. And how much will it drop? Well, it will drop given by this. Right, so you plug in numbers and then you'll find out, let's call that ΔV₁ actually. So you plug in the currents, which we learned in the first 30 minutes how to calculate currents. If they're given you the resistor, right? So they say R is 130, right? So you can plug that in. After you find I, right, you can calculate how much it drops over here. And then between here and here, nothing happens. So the potential stays constant. There's no potential difference here. And then between here and here, it will drop again. And how much does it drop? Well, it drops by IR, right? R2, that amount. Okay, I'm going to erase that because my graph is going to overlap. But you can calculate that. Okay. And from here to here, again, nothing happens because it's an ideal wire. Okay, so far the battery raises it and then it drops twice for these 2 devices. And then now this battery will raise it again. How much will it raise? Well, what is the EMF of this battery? It's also 1.5. Okay, so it doesn't have to be, but it is, in this case it is. So it will raise it by 1.5 because the battery is providing the energy, right? So it goes up. And let me just quickly complete the diagram. So here it's constant, and then this guy will cause it to drop a little bit more. So that would be 3, right? So it depends on IR3, like that. And it's constant, and then it drops. And the last one, it has to drop all the way back to the 0 point, because remember at the end point is the same as the beginning. Remember, this is actually wrapping all the way back, right? So the last point is technically identical to the beginning point. So this is called a potential drop diagram. So the name should be obvious why it's called that way. Right. 4. Okay, so this hopefully gives a graphical interpretation of what the absolute potential is doing, right? So actually, this is the absolute potential, and all the drops or rises is the potential differences. Now, this is overkill for a simple diagram like this, but I can actually just change one ingredient and make this a much more useful way to analyze. Is if I, actually, let me show you the final step first to complete this first. I was going to flip one of the battery around, and you'll see that it is much easier to analyze it with potential drop diagram. So the final step is, what is the use benefit of this? The benefit is now you write out what's called the potential drop equation from your diagram. And what that means is, when you add up all the potential differences, right, along the circuit, they should be 0. Okay, so if you add up the potential difference due to E1, the potential difference due to R1, the potential difference due to R2, the potential difference due to E2, the potential difference due to R3, the potential difference due to R4. So when you add all these up, they should be 0, right? Because, yeah, it should be obvious there. So what is the potential difference of E1 or epsilon 1? So it's positive E1, right? Now, for the resistor, it's going to consume the potential. It's going to make it drop. So it's going to decrease by I1 R1. And resistor 2, as you'll see in the diagram, let me put my mouse over here, is going to decrease it by I2 R2. And then now I move to epsilon 2, it's going to increase it by epsilon 2. And then so on and so forth. This is I3 and minus I4 R4, like this. So like I say, usually you'll be given all the batteries and you'll be given all the resistance. So the only thing you don't know, the last thing you need to find is usually the current. And because this is one loop, there's no branching out. So the current over everywhere should be the same if you want a steady current, right? Remember the traffic analogy. So basically all these are the same I. So you have one equation and one unknown. So you can actually go and solve I, right? So like I say, this is a semi-overkill way, right? You need to do all these 4 steps to find I for this simple example, but it comes into play with a more complicated one. Now, I'm going to show you the one with 2 loops in the next page, but before that, let me mention what happens if you flip one of the batteries around, because we're going to see that in the next example. If I flip this, so I will want to make this the long end and this the short end, like this. So this time, this battery, instead of providing energy, it's going to, because this battery is trying to move the current this way to the right. This battery is trying to oppose it to move the current to the left. Now they're competing each other, right? The second one is not really helping the first one. In fact, it's discouraging the first one. So instead of raising the potential, this guy will do the opposite. If you flip the battery, it will actually consume the potential. So this will actually cause a potential drop of 1.5. Well, if it's 1.5, then it goes all the way to 0, right? Then it doesn't. Yeah. So imagine you have 2 batteries facing each other. Then nothing is going to happen. So let's say this is a weaker battery. Let's say this is just 0.5 volts battery. It's a very, very weak battery. So it will, instead of raising it by 0.5, this time if you turn it around, it will cause it to drop by 0.5 before you complete the rest of the diagram like this. Okay, and in your potential drop equation over here, instead of putting a positive sign in this term, so this term over here, you will put an extra negative sign in front of it, like this. Okay, so that's how you deal with if you flip the battery around. Okay. All right, so now let's put this in the most complex example we can think of, like this, in the next slide. You also notice I'm changing my whiteboard to a white background because I want this to look as close to how you would solve a problem on your pen and paper as possible. So you know how to label stuff. So this, hopefully the screen mimics as close as possible to how you're actually doing the problem instead of a black background, which looks cool for teaching-wise. All right, so how do we do this with 2 big loops? So what you do is you first analyze them 1 loop at a time, okay? Because now we know how to analyze 1 loop. So just split this into two different loops and analyze them one at a time. So let's look at the top one and the bottom one. Remember, the first thing is you need to pick a starting point to linearize your diagram, right? To draw that potential drop diagram. So where is a good starting point? Let's look at the top loop. I usually like to start just before a battery, like this, okay? I like to start just before it because the battery provides you can start anywhere as long as you complete the cycle, but the battery provides the upward slope of the potential drop, right, diagram. So that's usually a good point to start. Let's start over here. In fact, that's called D. Might as well start there and move to the left, okay? So I'll directly draw the potential drop diagram. So the first thing I see is this battery. Now I need to give things names, as you know. Okay, so this is already given epsilon2, that's good. This is given little r, but there's two little r's. So let's label this R1 and R2. Okay. In fact, everything is going to be so crowded that I might just redraw this for convenience. And I encourage you, when you do your own problems, to try to always redraw your diagrams as well, because even sometimes, you know, all the different labels I don't really want, it's not really the best way to label things anyway. And it's better to create your own labels. So like this. So we'll plug in all the given numbers last. So epsilon1, and I'll work completely with variables first. R1, and let me call this capital R1. Actually, let me call this R1, R2, R3, R4. Oh, that's little r. There's no difference between little r or capital R, but yeah, we'll just use this. Okay, and I want to start over here. Okay, so this is first epsilon2, so we're gonna go around the loop like this. So let's call that loop number 1, right? And then we'll handle loop number 2 later. Okay, so we'll draw this out. So first it encounters R1, and then it encounters R2, and then it encounters R1 as I go along the loop, and then it goes back. Right, that's the end of it. Okay. So this is the first loop. All right, so how would it look? Well, it will start off first, it'll raise it by epsilon2 amount of potential, and then it will go constant between here and here, and then it will cause a drop over here. It will go constant, it will cause another drop, and it will go constant. And remember, at the end, it has to go back to where it starts. Okay, so after a while, you can actually directly write out, go ahead and write out the potential drop equation without the diagram. At first, you might find it helpful to visualize. After a while, you can directly write this out. So the battery provides this much, and then the first resistor consumes this much potential. At first, you might actually want to write one more step. So just add up all the potential differences of each component like this. And then you plug in the numbers. Okay. Now, which I, before I move on to there, which I should this be? Well, even ignore the diagram. Sometimes they label it for you, sometimes they don't. So you need to give it a name over here as well. Okay, so maybe I should write this down as a tip, as a problem-solving tip, is for each resistor, label Ri, for each battery, label epsilon I, and for each branch, label the current. I like this, for each branch. Because within a branch, the current is the same, so you don't have to label it for every device, every component, for each battery, and for each resistor. So here, let me mimic what is given in the diagram. I'll call this I3, and then I3 gets split into I1 and I2. So immediately, I actually can, just before I forget, I might want to just drop down this note to see that this relationship between I3, I1, and I2 like this, right? So I3 is I1 plus I2. Okay. So which I goes in here? Well, it's only it's I3 that is going through little r1. So we should put I3 over here. Plus, sorry, minus, because it's a drop. Every resistor will create a drop, right, of potential. So going to be, again, which I3, R2. Now, how about R1, right? R1 is also a resistor, so it'll create a drop. And then what is the current going through R1? This time is I1. All right, what do we know and what do we don't know? Usually I is the thing that we don't know, right? So if you see all the epsilons are given, all the R's are, all the resistance are given. So just to keep ourselves sane from all these variables, you see, I'll tick off the things that we know, and we don't know, there's two unknowns over here, I3 and I2, sorry, I3 and I1. Okay, so good thing is we have a second loop. Potentially, this will help us to solve it because with one equation and two unknowns, I can't solve it, right? So let's go to the second loop. I'm going to try to do this faster this time. I'll start with just before the battery, just like I said, and go around this way. It doesn't matter which way you go around. Either way will work if you do it right. Okay, so let me try to directly write it out. So at first you'll encounter the first battery, and then you'll encounter the first resistor, you encounter the second resistor, R3, and this time you'll encounter another battery, epsilon2, and first and little r1 and little r2 equals 0. And this is plus, right? I'll try to eliminate the brackets, plus epsilon1 minus, okay, which I should I use over here? I should use I2 in this branch, right? Minus I2 R3. This, and then here's the battery. Is it in the right way or the wrong way? Well, this is in the right way, right? So this one's raising the potential. This is also raising the potential as I move along here. So this is also plus. I don't need an extra negative sign. And minus, if the battery is in the right way, it's going to provide a potential boost. And then each resistor is going to consume that potential that it just created. So minus this time is I3, R1 minus I3, R2 equals 0. Okay. So let's imagine move this down here. Okay. So I have the first equation and the second equation. Let's take off, just to keep ourselves sane from all these different variables. What do we already know? Okay, so usually the R's and the epsilons are given. And now the only unknown is I2 and I3 over here. Okay. So what are all the unknowns? I don't know I3, I don't know I1, and I don't know I2. So I have 3 unknowns. I only have 2 equations. So how do I solve this? And so fortunately, we have also this connection over here, right? So now you have 3 equations, 3 unknowns. The rest is just plugging in the algebra, right? So since there's a limited time, I will just talk through it. So you can take this and plug it into say both of them. So now you replace all the I3s with I1 and I2, for example. There are many ways you can do the math. It's just algebra. So there's millions of different ways you can approach it. I'll just mention one, right? It's probably not the simplest one, but it's the most straightforward one. You take the I3, plug this in. So here there's only I1 and I2, right? Can you see that? And if you plug this in here, now there's no more I3. Everything is just in terms of I1 and I2, right? So now you can use your favorite elimination or substitution and eliminate the other variable and find what is I1, what is I2, and then find out what is I3. Okay. So this is called Kirchhoff's loop rule. So when you sum over all the components, and they should equal 0. If you would like jargons, this is called Kirchhoff's loop rule. I'm not going to write it down. And this is called Kirchhoff's junction rule because this happens at a junction. If you focus on the junction, you'll see that there's this relationship. If you look at a loop, you will see this relationship. Right? So there's names of this. However, once you understand the concept, it's not a. I think this is more important. I rarely even consider that's a law or a rule. To me, that's common sense that this gets splits up. So just stare at this and get that relationship out of that. Right? This, I guess, it's a rule. It's basically a conservation of energy if you think about it. Right? If as a charge moves through the potential difference, the charge is, remember, charge times potential difference is potential energy difference. Right? So it's basically if the charge is constant, this is basically saying you add up all the potential energy differences and it goes to 0. So it's a conservation of energy situation over here. Okay, all right. So the question actually asks for the potential difference between A and D. So that is actually a different thing it asks. So it's a little bit more advanced thing it's asking. Usually it just asks you to find all the currents first, and usually that's the first thing you have to do. And where's A and D? Okay, there. So what you need is you want to find the potential difference between here. So you can think of it as, first of all, the potential difference between A and D is the difference between here. So let me draw a graph over here, a bracket over here, AD. So you want the difference between here, right? So you can think of that as just adding up the differences between each of these points. I know it's a little bit difficult to see, but yeah. So so you can think of it as from first D to C plus from C to B. You don't always have the labels of the alphabet points, but since this one has, so that's easy to label, right? But if you think about it, between D and C over here, that's a battery. So this is actually going to be the potential difference of battery number 2 plus the potential difference between little resistor number 1 and the potential difference between the capital resistor, which I call R2 over there. Okay. So this one is plus epsilon 2 minus I3R1 minus I3R2. Okay. And you plug in the numbers over there after you find out what I3 is, right? You're given the battery and the resistance. You just need to find out I3 from the Kirchhoff's rules. And so what it actually asks in each problem is a little bit different, but usually it always starts off with you know how to use Kirchhoff's loop rule and then find the current of everything. Right? And then you can go and answer whatever thing they are trying to ask. Okay. The subscript says sum all the components, just I meaning 1, 2, 3, sum all the components in your circuit. Sum up all the potential differences in your components along the circuit. It should be 0. You can read the correct wording, the full wording in the textbook. Okay. The last thing I need to tell you is the concept of terminal voltage, and this is what I alluded on the first day. So let me just use the new slide. So the terminal voltage, now that you know how to look at potential differences, is defined as the potential difference across the battery's terminal. Okay. So if I draw a battery like this, what happens is inside there's the real battery part that generates the EMF, but there's usually some small resistance if it's not an ideal battery. So we usually denote this with little r. Okay, so one is the negative side, one is the outside. So this is the outside of the, this is the inside of the battery, right? So you can think of everything else that connects to other resistors as the outside of the battery like that. And inside there's usually some sort of resistance. And remember EMF, the electromotive force, which is not a force, it's actually potential difference, is defined as the maximum potential difference a battery can generate, right? Generates. Okay. So terminal voltage is the real potential difference that comes out of it. So what is the relationship between them? So let's call this VT for terminal. So it must be this plus this, right? So so you can say the terminal voltage is the EMF. I don't need the plus sign. The EMF minus IR, right? So or the drop due to the internal resistance. So that is IR. So the book might quote this as a very important formula. I wouldn't even call it a important formula. It's really just kind of common sense after you understand kind of how potential drop works. Does that make sense? Okay, so that's what terminal voltage is. So usually the symbols is we use little r for internal resistance, but once you understand this as a concept, when you actually handle circuits like what we just did over here, you just treat the internal resistance as any other resistance you work with. So you might see every time you have an epsilon, there's a little r that is much smaller in ohmage than the others, as you can see, because these could be like real device representing real devices, whereas this is actually representing the internal resistance that follows the battery. But when you analyze it, as you see with all my equations, it's no different from any resistors. So from a problem-solving perspective, there's nothing different. From a concept perspective, that's what it means. Okay. Okay, good. All right. Thank you very much for staying as usual, and have a good night.